As the slide says, I'm a senior project security engineer at Qualcomm. There, I work mostly on the software side and specifically on fuzzing. And before that, actually, I also worked on fuzzing in a brief parenthesis, doing vulnerability research in a company, just as an intern, but still I got a perspective of what was going on. And then I did a PhD on fuzzing as well. And this talk is actually not strictly about fuzzing in the technical sense, but more about the challenges and the differences that you encounter when you start working on fuzzing in a large company that manages a large amount of software, and how that compares basically to the other two environments. So I'm going to talk first a bit about security reviews and basically why you end up wanting to do fuzzing when you are in a situation like a Qualcomm. Then how fuzzing in such a situation is different from the other two, and then indeed a bit also about fuzzing infrastructure, because I think it's important. It's an important point that in this environment you need to care about, that maybe in the other two you don't really need that much. So first of all, I'll start with a principle we can all agree on, I think, which is that security reviews are necessary. And the reason for this is that when you have a privilege boundary like the one on the right, I'm not showing a more complex scheme because I cannot, but basically two components like that, CPU and NPU, probably are mutually distrustful. They have software, and there is software or firmware or whatever that runs on them that should not trust the input that comes from the other. And when you have a privilege boundary like that one, a security boundary like that one, an attacker that wants to cross from one component to the other may need only one bug to cross it, right? So in the end, when you have a security boundary like that one, you need a review to make sure that the security boundary is solid, because the security boundary is only as difficult to traverse as the bug is hard to find, basically. So you could, let's say, naively say we can just, look at all of them. We can just go check all of them. You hire a security expert and you go check the security boundary. Well, it turns out that there are really too many to check, or at least there are a lot. If you think about Snapdragon SoC, you think about all the hardware components that are in there, and then you think about the software components that run on there, and usually there is at least, a kernel and a user land that also constitutes a security boundary. And then now zooming out from the Snapdragon SoC, the company also has multiple products. Obviously they reuse similar components, but they are maybe combined in different ways. And the software is structured in a way where basically you have a development branch, but then each project is forked out of the branch. So the software that ends up in each software is different, and different generations of software may have received different bug fixes, or they have different features but the same bug fixes. So maybe the bug fix unmasks another bug that maybe in the newer generation is not present. And finally, on top of all that, you have code that is constantly being added. So as I said, a bug fix that is cherry-picked on an older branch may unmask a bug that was already present, or may introduce a new one that maybe in the new generation is not present. So really, you cannot just hire an army of security experts and go look at all this, because it's definitely too expensive. So the only thing you can do to try and manage this is to use automation. So really, you end up on using fuzzing and automation techniques because of to try and manage the cost of all this. When you look at automation techniques, this is a rough simplifications. There are things that fall kind of in the middle, but basically the classic division is that you have static analysis techniques that are used to analyze source code. They analyze the actual source code usually, and let's say for commonly deployed solutions is some variation of you have a bug pattern, you can define a bug pattern, and you look for that bug pattern in your code. This produces false positives that you have to process, and Qualcomm does this. But I'm an expert on the second part, so this is what I'm going to talk about. And the other one indeed is dynamic analysis techniques that imply that you build and run the software, could be modified with instrumentation and so on, but you usually run it and observe its behavior. If you do it correctly, there are no false positives, because a crash when you run the software means that there's a bug, usually. In the end, commonly dynamic analysis means some variation of fuzzing with some variation of sanitization and so on, in, let's say, commonly deployed setups. So fuzzing, by the way, I just want to mention this. It's, I assume most of you know, but it's a variation of random testing. So you just feed random input to the software, plus you have heuristics and feedback loops to try and improve and guide this random testing. But basically, it's just about, or at least just about feeding random data to software and see if it crashes. I wanted to have this as a small technical portion, but this is as technical as it gets, because you'll see this is not the technical part is not the difficult part. So as I was mentioning, I'm going to talk about how fuzzing in a large company is different from academia and from when you do offensive research. The first part kind of the fuzzing process. So when you try and start and develop a fuzzer, looks kind of the same, a bit differently from academia maybe, because you usually start from a working fuzzer. So you already have your fuzzer that works, has the possibility to accept feedback, and so on, produces random data without trouble. It fits your target. Usually what you end up doing is writing the harness. So you need a way to attach your fuzzer to the software component you are trying to test. And this implies, yes, the harness, so let's say, calling the API correctly, passing the random data in the right buffer and so on. But there is a significant part that is often overlooked, which is all the stubs and let's say the mocking, using a testing term, that you need to do to extract your target and separate it from all its dependencies. And you will see this is usually the hard part. So anyway, suppose you write all this, fine, you get a working fuzzer, you find some bugs, you hopefully report them to the developer for that component. And this is, well, this is where the process kind of, it doesn't really end, but it diverges significantly from the other two environments, because in academia you would probably go write your paper at this point. In offensive security you will probably go write your exploit. Here we need to go and try and push the harness upstream. This is extremely important because, as I was saying before, we need to go review the security boundaries, find basically all the bugs, but we care about both the ones that are continuously introduced, but also the ones that still need to be introduced. So what if someone 2 months after or 1 year after your review actually introduces a bug? You want to be able to catch that bug as well with hopefully with automation. That would be great, right? So you need to push your harness to the code base, and then hopefully manage to integrate it somehow in a CI environment that always pulls the latest commit and tests it, right? So you can imagine this is essentially a development task in the end. It looks a lot like when you write a test suite, right? More or less. So looking like a development task, then the problem becomes, okay, who should do it? How should we organize the harness writing process? Well, it's a development task, right? So you would say, okay, let's use developers to do it. They are probably good at it. This is a great solution in theory, because you have security experts that can come in, decide when a fuzzer is needed, because they evaluate the risk of the specific component, say, okay, this is probably a dangerous thing that we should probably test. Then they can tell developers to go write the harness. And this is great because it scales with the amount of code. So you have developers to maintain the amount of code you have. So you have enough developers to go write the harnesses. This is, in theory. Does it work? No. The reason is that developers work mostly on tight schedules. So their incentives are not really aligned with an effort of this kind, because they are usually evaluated on some variation of how many features they deployed and if they work correctly, right? So go and writing your harness is probably going to put them back on the whatever schedule they have, and it's also not gonna buy them much credit, let's say. So apart from with the security department, but it matters up to a certain point, unfortunately. So and the last point is that they also need to be trained to writing harnesses, because I said it's similar to writing, let's say, a unit test, but there are certain peculiarities that you need to be aware about to make the fuzzer work correctly, achieve high coverage, and be able to monitor it correctly. So, okay, developers proved not to be really an alternative. The department tried this, and the result was that the training efforts even didn't really gain traction, and we got a lot of pushback from developers. So it's 2025. I wanted to have this because it's I think it's relevant. So can you use AI to generate harnesses or some variation of an automatic generation technique? Well, there is research in academia about this, but it works, I think, very well with open source software that is meant to be used without interacting directly with the maintainers. So it's well documented, and has probably well-defined interfaces, at least, the successful one. The problem is that when you work instead with proprietary code, you are doing a security testing, basically, you're probably ending up dealing with the worst code the company has in terms of quality. And so apart from being probably buggy, and that's why you're looking at it, it's also probably not well designed, which means it's also probably highly coupled code that has lots of interdependencies with other stuff. And writing the stubs, as I was mentioning before, then becomes the difficult part. So this thing, as far as I could see in my research, it's currently out of scope, and it's also in general difficult to deal with, and I understand. In terms of Gen AI, does it help? As I was saying before, it's a programming task, or a development task. So yes, it can help, but stubs are a problem here as well, because the difficulty usually doesn't lie in writing the stubs, but in getting the information regarding what should go in the stubs. So the documentation could be sparse, and you could actually need to go talk to people to understand how a certain thing works, because indeed it's not open source, it's not handoff. In theory, you can go talk to the person, so the model cannot really do that easily, let's say, so retrieve that information. So we are left with one not ideal option, which is that security experts can do it. This is not great because you usually don't have a lot, so it doesn't really scale with the amount of code you have, but at least you can prioritize and go look at the most dangerous things, the ones that are more likely to be buggy, and this, does a pretty good job at the end of the day. At least they don't require additional training, or at least the training is easy to do because they have competencies that fit let's say, the problem. And then you can involve developers only for clarification and what I was saying before, when the documentation is not clear, so you waste a bit less of their time. And at least finally, you end up with a working fuzzer, you find some bugs, you report them, and that's okay. However, as I was saying before, this is not the end of the story, because you end up with a fuzzer that is running on your machine, but who maintains it at this point? So is it security experts? Is it developers? Well, maintenance. So this is code. It's maintenance. It's, based on a thing that should go in a code base, and it looks a lot like a unit test. You would say, okay, maybe developers should do it this time, right? So we already did the job. We built the fuzzer. They just need to review it and then maintain it once it's inside their code base. Does this work? Well, sometimes, or even often, I would say. There are a few positive factors and one main negative factor that I could identify in like the success and failure stories I could gather from, well, myself and my colleagues as well. So, well, when you have support from higher levels of management, then, okay, it becomes easy because reviewing and maintaining your fuzzer becomes just a new feature they need to support. The developers need to support. So then the problem is solved. However, this is hard to get. One additional thing that helps is when the developers already have a well-structured test suite with a lot of unit tests. So the harness becomes just one more unit test for them to maintain and to adapt to when they change APIs and stuff. And so these two things, well, basically, once they have the unit test, they are probably more willing to just put your harness in. One main negative factor is that you just hit them with probably 20, 30 security bugs, or at least bugs that need to be fixed for the fuzzer to run. Because when you run a fuzzer, you are the first one who writes the harness, then and you're looking at a piece of software for a reason. You usually just find a lot of bugs immediately at the beginning. And when you end up in this situation, you want those bugs fixed as soon as possible. So that puts, when you report the bugs, that puts developers on a fairly tight schedule to actually fix the bugs, immediately. And this is kind of an interrupt in whatever they were doing, right? So, maybe they waste one week, 2 weeks to go and look and figure out the root cause and fix all the bugs you reported. But at that point, you already put them 2 weeks behind schedule on whatever they were doing. And at that point, if you go and tell them, okay, look, and now you should, review and merge my fuzzer, they're probably going to tell you no. Personally, I was in such a situation, and I did exactly this. So I put them, 1 week, 2 weeks behind schedule, and the reply I got when I told them that they should review my fuzzer was that they would do it, but in 6 months when they branch the new product. So I should, wait 6 months, then wait for the code base to stabilize for the new product, rebase my stuff on top. And then they would, do the review, because at that moment they were just, fixing bugs basically and making sure their software was running for the current generation. So not great, but sometimes it happens. One thing that works very well though, is relying on dedicated testing teams. So at Qualcomm, we have these teams, not for all components, but so obviously we do, unit tests, and that developers take care of that. Then we do QA, and integration, like more, let's say, comprehensive, testing that spans over multiple components. But then we have dedicated testing teams for certain critical components that are either security critical or just very difficult to test or very complex. So think about kernels, compilers, this kind of stuff. So they're not always present, but when they are present, they work very well. as a basically to help in this process, because they already have the setup and the experience in triaging issues. For example, they already have the setup with the right physical devices and so on. And this with a company that produces a lot of different devices can be an issue, like getting the right device shipped to you to test whatever you needed testing. And the other thing they know is what product is going to which client, or which branch is going to which client and when. This is actually a very important information that is like you can retrieve as a security expert, but obviously if you have someone that already knows what should be fuzzed or tested and when and takes care of that, that's a great addition. And we have aligned incentives finally. So we both find bugs because they mostly focus on positive testing functionality, probably, and the security side mostly focuses on negative testing. But their metrics, their incentives are probably going to be some variation of bugs found and fixed, or let's say improvement on the quality of the code and so on. So the fuzzer is likely going to help them as well reach their goals. So they're usually happy to help, and they are able also to monitor the tools and help with triaging the issues. So then security experts can be pulled in again only when major changes happen to the API, and then you need to fix either the harness, the harness, it depends, or major changes to the harness, to the API, or to the fuzzer itself if it's something custom. And sometimes it just doesn't work. So sometimes you don't have the testing team. Maybe the component you checked is not important enough to be worth the effort, like the thing I was mentioning before of, in 6 months picking up the project again, rebasing and working with the developers for the review. So at least there's a starting point for someone else that will need to conduct a review in the future, because it will need to happen again. And at least you caught some security bugs, but obviously some stuff may sneak in that is introduced in the meantime. But sometimes this is all you can do. Still, now I wanted to talk a bit about fuzzing infrastructure, because I think basically this is an interesting topic, because you cannot really rely on, so when you run fuzzers, you cannot really rely on the testing infrastructure that is commonly available for test suites and so on, because fuzzing forces you into sort of time-based campaigns. Usually they are set by the rebuild frequency or rebuild period. So for example, you have maybe nightly rebuilds of the software when the tip of the development branch get pulled in, and you need to make the most out of the time you have available, because performance is a critical thing in fuzzing, and specifically this means how many iterations you can perform per second. So you need to make the most out of the time you have. You probably need some more let's say powerful infrastructure to do that. And while there is some overlap with the normal testing infrastructure, like for example figuring out automatically when a certain bug was introduced, which versions are affected, and so on. So this is all stuff you care about both in testing and fuzzing. The normal testing infrastructure usually it's not suitable. So what you end up doing is you can either roll your own, and there are companies that do that. This is problematic in certain situations, because security experts are very good at breaking stuff, but not necessarily at building it or maintaining it. So you end up with maybe software that is supposed to be very reliable, because this is running a very intensive process, a very, let's say, high, very demanding in terms of resources processes. and can be broken very easily because the fuzzer may not be contained correctly or things like this. So that has drawbacks. Or you can go the route our department took, which is to try and rely on open source software. And this actually worked very well because we are running our own private ClusterFuzz instance, and this is some of you probably know it's a project, an open source project from Google, and we basically, the department managed to run it privately with taking care of all the concerns about IP protection and so on. And we managed to adapt it for our needs quite well. So that paired with a custom instance of OSS-Fuzz that doesn't look like OSS-Fuzz much anymore, but the build pipeline looks more or less the same. So you can indeed use those two pieces of software, and you are able to fairly cheaply obtain building and fuzzing infrastructure that works without writing it from scratch. The only issue we encountered is that it's very much libfuzzer focused. For those of you that don't know, libfuzzer is the fuzzer that is integrated in LLVM. It's very commonly used just because it comes for free with the tool chain that the developers are probably using. So you have it in the build containers already and so on. So it's a very easy thing to pick up, and this is why it's used the most. But it doesn't fit. So one, it's not receiving major updates anymore. It's more or less in maintenance mode at the moment, and it doesn't really fit more complex targets where you want some more custom things that maybe you're implementing with probably libafl or other specialized tooling. It's a bit more difficult to integrate libafl based fuzzers in ClusterFuzz. It's feasible, but it requires a bit more work. That's the only, let's say, paper cut in the experience. The alternative is working with dedicated systems, and we do this for everything else, and everything else is a lot of Syscaller instances, mostly, because as you can imagine, we write like the company writes lots of Linux drivers that are going to be tested with Syscaller. And you need the actual, or often you need the physical device to test these things. So you probably want a machine you can plug your physical device into. By the way, Syscaller is a very good example of the thing I was talking about for dedicated testing teams, because there we managed to offload running these Syscaller instances and these dedicated systems to the testing team for the Linux kernel. And the security department basically helped writing or wrote most of the grammars for Syscaller, which is a grammar-based fuzzer. So you need to describe basically how the API looks like. But then we, like the security experts indeed get pulled in only to update the grammars, which are fairly stable. So most of the effort is not on us, and we can go, work on different things. So, this was more or less, it. I am very curious to know if someone had similar experiences, worked or has dealt with similar problems. So, and if you have suggestions or similar, come talk to me. I'm curious to know what others experience, because in my opinion, this is like how to make this work effectively is still an open problem, and you need, failure, as I said, is failure in, let's say, not fuzzing, but more like in integrating fuzzers and have them running is always a possibility. So I'm curious. Apart from that, I'm happy to take your questions. So and thank you for listening. Yeah.
Maybe time for one quick question before lunch.
Yep.
How do you measure progress and report it?
So the question is, how do you measure progress and report it? There are metrics that get monitored, and this is mostly so one easy thing, one proxy metric that is actually used in academia a lot is code coverage. So you go grab your software, you run your fuzzers, you collect your corpora, and then you try and estimate. Well, you basically figure out how much of your code was covered. There are issues with that though, because then you have components, and you have this a lot with the kernel modules. So maybe a lot of the code that runs is run during initialization. So then you have a manager that comes and says, "Oh, look, you have 40% code coverage. Why is that?" Because and that's mostly because the IOCTLs, which is maybe the part you care about, that's covered pretty well. But then most of the initialization code is maybe not covered, and then you need to go and explain. So really, my answer is I don't have a clear answer. This is a difficult problem as well. Yeah, and indeed, like reporting code coverage and then explaining how it should be interpreted is what we go at the moment. The alternative is you try and shove in initialization, into the code coverage as well. So it doesn't really mean tricky numbers. It's more like making them more representative for someone who's not knowledgeable about what is actually going on. But that's another alternative. And yeah, but still, I have no real definitive answer about this as well. Yeah.
Let's think about it over lunch.
Yep.